One person dies in the United States every 34 seconds due to disease, and 80% of these deaths are preventable. People in underprivileged neighborhoods might not have the access they need to emergency and expert medical care, and many of these same people might not have access to a physician or cardiologist. Medical healthcare providers may be able to run basic screening tests, but many of them might not have the expertise required to properly diagnose heart disease. We know that early heart disease diagnosis, is the key to saving lives and reducing the effects of heart disease. So what if we had an app that just by putting in some basic medical parameters could accurately and fast diagnose heart disease? And that's exactly what I've done, predicting heart disease using machine learning. Hi, my name is Aditya Naravane from North Attleboro Middle School, and sadly, I am no stranger to cardiovascular health. 3 years ago, my grandfather was having chest pain, and luckily he had access to urgent and expert medical care. 2 angioplasties later, he's feeling healthy and doing well. This sort of problem lends itself really well to machine learning because it has large datasets and clear, well-defined rules. Once trained, this network will be able to be used to triage cases so that urgent cases get the help they need faster. So, this is the final product of my app. It has 12 different parameters that the doctor or patient can enter in. And on each one of these parameters, there is an info button that allows them to get more information if they need it. There's also a data tab, so if you want to see the data that it was trained on, you can see it and compare it to the other data. So, back to the prediction. I've put in some data from my dataset, and this patient did not have heart disease. So, once I enter it in, it says, heart disease unlikely, correctly predicting the patient's diagnosis. One of the existing solutions used for this problem is websites such as WebMD, which help you see the symptoms of things, but it relies on patients self-diagnosing, which is less accurate. Other methods are used like biomarkers and genetic testing as well, but these are mainly used to see the risk of heart disease and not the actual presence of it. A feed-forward multilayer perceptron is the type of machine learning that I chose to use. It is made up of one or more layers of interconnected neurons, with each neuron in one layer connecting to every neuron in the following layer. The network processes input data by passing it through the layers without any feedback loops from the input layer to the output layer. Each neuron in the hidden layers does a linear adjustment on the input data before applying a non-linear activation function, such as a sigmoid or ReLU function. The output of each neuron in the hidden layers is then given as an input to the next layer, until the network's prediction is produced by the final output layer. During training, the network uses backpropagation, a type of gradient descent optimizer, to alter the weights and biases of the network in order to reduce the difference between its predictions and the true outputs. By generalizing, it's able to understand the patterns in the data and making predictions on future inputs. I tried out several libraries to try and create neural networks. At first, I tried to make it using just a math library and doing all the coding myself, and I found that was incredibly difficult. Then I tried out 2 libraries, TensorFlow and Keras, but I found that these 2 were also very complicated and lacked tutorials for what I was trying to do. Finally, I tried out PyTorch, which was much more simple and had plenty of tutorials for what I needed to do, so I decided to stick with that. The dataset I decided to use is the Heart Disease dataset by David Lab. It has over 1,000 rows and includes 12 different parameters the network can take in, such as blood pressure, chest pain type, length of ST segment, slope, and cholesterol. Once I got the dataset, I started training the network and testing out the different hyperparameters. I found that the best optimizer for this application was the Atom optimizer. Stochastic gradient descent wouldn't work well and would actually increase the error at times. For the amount of neurons, I found that between 128 and 256 neurons was the best. It drastically decreased the error as you added more neurons, but at a certain point it would take far too long to train, and the network would not have enough data to properly adjust the weights and biases for all these neurons. It was much the same story for the amount of hidden layers, as the error drastically decreased after 2 hidden layers, but at 3 and 4 hidden layers, it reached near 0, and it had a problem generalizing for for the new data coming in. And also, it didn't have enough data to properly adjust all the weights and biases. So in the end, I decided to go with the Atom Optimizer, 256 neurons, and 2 hidden layers. This is my code for the neural network. First, it imports the data and splits it into a test and training dataset. Then, you define the neural network with 2 different hidden layers. Then you define the model with 256 neurons. You define the criterion, which is the loss function, which tells you how correct your network is, the optimizer, and then I train the network using the training data. First, I use the model and I give it all the inputs from the training data set, and I get the outputs, calculate how correct the network is, and then optimize the values and run that through until it's reached the epochs count and the error is low enough. Then I test it based on the test data to see how correct it can be on data it's never seen before. Finally, I export the weights and biases to my GUI. This is what my GUI looks like. So, by running it, you get the GUI opened. It has 12 different parameters that the patient or doctor has to input, and if they need it, there are information buttons on by each of these to see what they mean. By entering in these values, you can get a prediction from the network right here. Also, if you want to see what the data that the network was trained on, you can in this data section. I talked to an expert, Mr. Benzie Miller, who was kind enough to share with me some advice. He told me to look into the data I was using, and also that I could look into the Framingham Heart Study for better data. He explained me some issues with the heart, some common risk factors, and how the heart works. He also told me that nurses and doctors in Europe versus America have vastly different procedures and data points that they use, which could be an issue if I was planning to use this across continents. In conclusion, the neural network ended up being very successful. It had an error of less than 1% and was able to be easily exported to the app. And the app worked well as an interface for the network and was easy to use. It could be used in screening, home use, quicker diagnosis during checkups, and identifying key factors in heart disease. However, this project is not perfect. It's not been approved by any medical professionals, and the data points might not be applicable in different parts of the world. In the future, I would like to look further into the risk factors of heart disease and maybe get data from more reputable sources, such as the Framingham Heart Study, whom I have reached out